Okay, lucky you, last session. So I just need about, let's say, 10 to 15 minutes, and if you don't have questions, we can go all have a drink. But before that, are you ready to talk about cabling? Because we're talking about quantum stuff, software, everything, but what needs to happen in the fridge is to connect usually electronics with particles in order to make computation, but we tend to forget cables. So let's talk a little bit about cabling. So Viqthor is a small company that is about a year old. We are, as you'll see, 7 people, and we're working, targeting the control of the qubits, not only the electronics, but also going down in the fridge. So I'll show you exactly where we are. As I said, we are 8 people. 3, actually, we work for like 10 and 20 years together. We were very active in the microwave industry, testing radars, satellite payloads, clocks, and all these things, plenty of microwave cables, low-level signals, and we decided to go into quantum. So the team is of 8. We're actually located in Saint-Germain-en-Laye, just west outside Paris. And today, so we're going to tackle a few problems about quantum computing for superconducting qubits. First, as you know, the quality of the qubits is a lot of stories about noise. Well, we come from a middle where we talked a lot about noise, cancel noise, extract noise, compensate noise, and wiring. This is the key factor. This picture is for, I think, about 50 qubits. So let's say we want a cable of 1,000,000 qubits. It's going to be strictly impossible. So you can make different things. You can make ribbon cables. You can try to do a lot of things, but it's going to be very expensive also. Because for each qubit, you're going to need some electronics to send signals, measure, and multiplying these electronics makes it very expensive. Like, let's say 100 billion euros for a processor of 1,000,000 qubits with a power consumption of, let's say, 50 megawatts. 50 megawatts is like the biggest solar farm that exists. This is ridiculous, especially for the environment. By the way, Viqthor is a company that aims to reduce the power consumption of QPUs in the future. So we decided to try to do some noise cancellation technique like you would have in your earphones, and also multiplex signals so you use less wires. And actually, if you want to use less wires, you can also go on photonics. And all this because you multiplex, you got less hardware, it's lower cost, and it uses less resources actually on the planet. So the key things are using multiplexing to address with one media, one transport channel, multiple qubits. Use photonics for the cryostat because you all know that a fiber is much lighter weight than a coaxial cable. You also know that at home you'd rather have fiber than DSL because of a bandwidth. So photonics is very interesting. And noise cancellation because we need to improve the qubit quality. So as you can see on the left, you got a cryostat, let's say, with for 53 qubits with a lot of cables. If you take about the same kind of configuration and you say, I'm switching to fiber, this cryostat is equipped actually with devices I'll show you later, with fibers, and we aim to control 10,000 qubits on a single fiber. And it has some techniques, of course. Everything is in the multiplexing, but it's also much lighter weight, so the heat load for the cryostat is much lower. So how do we do multiplexing? You may know that, okay, if you want to tackle drive 1 qubit, you're going to send some pulse shape at 1 frequency to the qubit. Let's say now they don't react all the same, or they have filters to select their own frequencies. Then you can send on the same signal, on the same cable, multiple signals. And that's called frequency division multiplexing. That's what we create in microwave with our DACs, with our software control. Then you can print those waveforms on light. Light with a color. If it comes from a laser, you might have a red, you might have a blue, a yellow, whatever. So you can do that multiple times. So you would do a 2-dimension multiplexing of a signal. And this is what can take you to up to 10,000 control signals per fiber. And this is a lot. This is huge difference because now if you want to scale to 1,000,000 qubits, then you could say, okay, if I got 10K per fiber, I put 100 fibers and I'm done. Now, of course, you need to do the qubits, the chips. Now, about noise cancellation. This is obvious. If I take a sine wave, I take the opposite, I sum, I get 0. Now, if I have a sine wave with noise, and somehow I can extract the noise itself, then I can subtract this noise and recover my sine wave and improve a signal-to-noise ratio, as we say in microwave, or the quality factor of a readout of a qubit, for example. So those 3 points are the points that we are putting in our system. We have other features like time synchronization. We don't need to synchronize everything because as we do multiplexing, we can transmit synchronous signals at the same time through the same medias. We don't need a lot of synchronization. We also have optimization software for making the waveforms very easy to, let's say, transmit through non-linear devices or devices which are limited in linearity. But this is not the most important. Now, if I show you exactly what we are going to release this year, so this is kind of a preview. So we are going to, of course, as I said, use fiber optics, so be able to transmit a lot of links from the room temperature down in the cryostat. You can see the room temperature electronics and the ice cube, which is a small device that's going to fit in the fridge and recover all the microwave links that you want to output to qubits. We also have our digital pulse processor, which is kind of what you could say the baseband that creates the waveform, the shapes, and this you can control. It's running real time. Waveforms are generated within our FPGA, and you can have, let's say, 40 outputs on this chassis to control, and then some readout channels too. We also have to be able to access some technology. Of course, all qubits are not at the same frequency. Some of it will be at a few gigahertz, some will run up to, let's say, 17 gigahertz. So we have developed also a huge improvement for our strategy is that in a chassis we can plug a lot of up and down converters. See those blue and red devices? Those are up and down converters, and each of them is fully autonomous. It has everything it needs inside. You just inject an IF, recover an RF out, or vice versa. You inject the RF and you recover an IF. And this is all independent, so you can control all your qubits in the different fashions. Now, the impact for the cryostat, if you, again, look on the left, let's say you have 192 cables. Then if I take those 192 cables and I switch with the ice cube and the multiplexed solution, then you can control up to 4,000 qubits with this cabling that's shown on the right. And this is extremely efficient. Now, if you say, I can do 4,000 with this architecture, then I can scale it up later and go up to 1,000,000 qubits. So this was a quick talk, so then you can go enjoy your drinks at Quantonation in the 10th arrondissement in Paris. But of course, if you have questions, I welcome them.
Perfect. Thanks very much, Guillaume. That was very interesting. So, yeah, as usual, if there's any questions, please get them into the app. There is one. So, you mentioned the patent pending technique for the noise cancellation in the waveforms. Do you think there's any scope, or does it make sense to use any machine learning techniques with that, or you can scram machine learning in everywhere?
This is a very good question. No, this is a very good question. Actually, we are discussing one of the key things is actually how do you extract the noise, because you want to subtract it. It's not something that can be statistical through time. So it's like some people said you could average, you could compare and learn some model, but models would be statistic distribution and stuff like that. They wouldn't enable us to in real time suppress exactly each modification. So you need to extract. And extracting real time, I mean, in the past, we've done it for, let's say, defense projects. And this has always been done more or less in an analog way to have real time output.
So it's almost a data problem in the first place as well.
Yeah, but I mean, I don't think AI will have a problem because it's going to be based on distribution, on statistical analysis.
Sure. Okay.
I might be wrong. I mean, anyone who has a question can ask me again.
Perfect.